The first thing I would like to say is a big thank you to Radu, Jura, Robert Chesnek for running the One World Optimization seminar during the pandemic, which was an amazing thing that brought all of us together and was really the main optimization seminar. So that was absolutely wonderful. It's wonderful to be together again here in person now, from all over the world, despite everything else happening in the world. So again, thank you. I would like to say that some of you may have heard this talk because I gave a very similar talk in Antwerpen recently, but hopefully there is still something of interest. This work that has taken me a few years to develop with my team, so I would like to acknowledge my former postdoc, Estelle Massar, a PhD student at Dileto Temisov, and master student, Sinzu Liang. And our goal was rather ambitious. I was very worried about the scalability, and I still am, of global optimization solvers. So throughout my recent work, some of my recent work, we have tried to see where are the areas in optimization where scalability of algorithm is poorest and is most poor, and where we could do some things to improve it. And essentially, the biggest, hardest of them all, of course, is global optimization. So what can we do there with some simple ideas, rather conceptual, that we then try to see how we can improve general solver scalability. Of course, global optimization is NP hard, and so with this comes the question of tractability. So at the same time as improving scalability, I'm looking for problem instances where these techniques work most, and we can get actually tractable classes of problems. So the idea, of course, is to do some kind of dimensionality reduction of non-convex, possibly black box problems given to us. And the simplest is I want to find a matrix A that projects, that encodes my input X, my parameter domain, into some smaller dimensional subspace R little d. So I'm going from R big D to R little d with some matrix A. Maybe I do this projection once, maybe I do it multiple times, but what I'm trying to do is then to just solve, say, my problem. Instead of solving in X, I'm going to solve in Y, and Y lies, as I said, in a much smaller subspace. Hopefully I can apply in the subspace any global solver. In the subspaces, global solvers, in small subspaces, global solvers should do just fine. So this is not a novel idea. It's just random subspace methods, essentially, or non-random. It's just some subspace methods. So here's a very, very generic framework. I draw, say, a Gaussian matrix at every iteration of my algorithm Rego. I draw a matrix K, AK, that projects. So in this framework, it's a random matrix. And then I solve my reduced problem. So I solve at every iteration this reduced problem in Y, and I may or may not have some box constraints here, so it could be unconstrained or box constrained, and I may have a bit more flexibility by having a so-called current iterate PK here, which is just like an anchor point at which I draw my subspace. So, and then in the subspace, I do, say, approximate or probabilistic global minimization of this small dimensional subproblem. Then I find, say, a better point in this subspace, and this is my next major iterate. Then I draw my anchor point, and I choose my dimension of the subspace. Can be the same as before, or I can change it. This anchor point can be exactly my best point found so far. So I start from a point, I draw a random subspace, I solve in the subspace, I find a better point, I draw another subspace at that better point, but I allow some flexibility if I want for some reason to always draw the subspace at the random subspace at the same point, that's possible. So what can we say? Well, if F is Lipschitz continuous and there is a global minimizer that's attained, and then each subproblem is solved to sufficient accuracy, and for a variety of choices of these anchor points pk, I can show that with probability 1, the best point found in the subspace will enter an epsilon neighborhood of a global minimizer. So I have this epsilon in the function space neighborhood, and then I can show that this best point found in each subspace enter this neighborhood almost surely. So the proof relies crucially on what happens in the reduced subproblem. So what we've done is that with every random draw of the projection matrix A, I reduce my original problem to this subspace problem. And then what we can do, given that F is Lipschitz, I can look at a ball. So here's my X domain. Here's a ball around the current X star. And I'm trying to intersect this ball with a random subspace drawn at a point P. So I have to quantify the probability of success of this phenomena. Once I manage to intersect the ball with this random subspace, I assume I have success in my subproblem solve. I will be able to find my global minimizer. So the whole problem becomes, what is the chance of this succeeding? And this is what we have to quantify. And we have to quantify this independent of the anchor point P. And we use stochastic geometry and transform this problem into a problem in stochastic geometry. And that's how we can bound the success probability of this subproblem, which then defines the success of our algorithm. Because you can think of the algorithm as having failure of intersecting this ball with the random subspace until the first success. So it's more, think like a geometric distribution, simply said, okay? Failure until success. And the probability of failure is, or success is what we can quantify with stochastic geometry. So this subproblem here is successful in the sense that that there is a global minimizer of my original problem that lies in this that is a minimizer of this problem with a certain positive probability. But of course, when we try to quantify this with asymptotic analysis, keeping the dimension of the subspaces fixed but growing the ambient dimension, we find an exponential term in there that depends exponentially on the ambient dimension, of course, because it's NP-hard. I'm just solving some very general optimization problem here. However, yeah. So you over p's, we can play around with the p's more maybe. The y's I have to minimize. Sorry. Yes. Well, this I'm only considering, I'm only considering linear constraints. Yes, so bounds. I'm only considering bounds. Yes. Yes. So this would be even harder if I didn't have bounds here. Yeah. So in the unconstrained or the bound constraint case. So basically, this is it's a pessimistic bound because we try to have it for all p's and so on. So I think things could be improved here a little bit. But anyway, this is better than say uniform sampling or doing random search on like one-dimensional subspaces. So fine, but this is kind of the general framework. I haven't assumed very much about my function f. So things are still very bad and pessimistic. Can I apply it? Yes, I can apply it. I can take some global optimization problems and just solve in random subspaces with my favorite solvers in each subspace. I can still have a method that will be fine. However, provably, it's not going to give me, in terms of dimension dependence, of course, it's not going to give me anything else but exponential. However, when are these methods particularly good? For some special structure problems like these functions with low effective dimensionality. So what are these functions? Well, I would like you to have in your mind this stretched sinusoidal curve. So in this simple drawing here, you can see that the function changes in this direction, but it's constant in the orthogonal complement. So anything interesting from an optimization point of view happens in a lower dimensional subspace, and the function is constant otherwise. So in other words, if I have an over-parameterized model, for example, it's very often that the model will not change when I change some of the parameters because it won't react to changes in all the parameters. Now, if this lack of reaction is linear, then or affine, then I get this kind of structure. This is the simplest structure that we will show that with subspace methods can be made tractable. You can then go on to more complicated things maybe. So these functions, these functions with low effective dimensionality are also called low-rank functions, functions with active subspaces, multi-ridge. They are present a lot. There's a lot of discussion about this in different areas, including machine learning. And hopefully, I get to say something about that at the end. So what happens in the unconstrained case? So if I want to minimize globally a function with low effective dimensionality and I have no constraints, then if I draw a random subspace that has the dimension at least the same as at least as much as my effective dimension. So if I know my effective dimension and I draw a random subspace of that dimension, then with probability 1, my random subspace will intersect a subspace of global minimizers. So what happens interestingly in these functions is that for every global minimizer, I have a subspace of global minimizers because of this invariance. So this helps me hit it easily with a random subspace. That's basically the idea. So in fact, if I know this ambient, if I know the effective dimension, as I said, I only need to draw one random subspace. So I do one random projection of my problem, I solve globally in that, and I'm done. Of course, I may not know this effective dimension. So of course, I hope it's clear that my underlying assumption here when I say I assume there are these functions with low effective dimensionality and this is what I'm optimizing, I don't know this effective subspace. If I know the effective subspace, the problem is trivial, right? So I'm assuming here that I do not know it. I am not going to calculate it explicitly. If I do, so if I have an unconstrained problem, then and F has this low effective dimensionality with effective dimensionality dE. If I know this, only one random embedding. If I do not know it, start with anything you want, like two-dimensional subspace, solve in it, grow the dimension, solve again, and keep doing that. You will stop after at most dE embeddings, random embeddings, you will stop. You will just see that your function doesn't change anymore, doesn't decrease anymore. In all these cases, the success probability of this reduced problem that I show you, we can show that it's independent of the ambient dimension D. So we get tractability in this case. We can fully quantify where the reduced minimizer lies that corresponds to a minimizer in the original problem. We can give a precise random matrix theory bounds on the size of this reduced minimizer corresponding to an original global minimizer, and that would allow you even to make your subproblem constrained, which you do want in global optimization because many global solvers are, say, branch and bound and so on. So essentially, all these probabilities of success are independent of this M here is only dependent on the effective dimension of the subspace, random subspace that you draw, and does not have ambient dimension dependence. So here are some numerics. So I took this simple framework and I applied Baron. So what we do, okay, you may ask, to what test set? How do you know it has this special structure? Take any global optimization test set, append fake dimensions to it, append zeros to artificially increase the problem dimension. Then rotate your coordinates with some random matrix. Because if you don't do that, then always your effective subspace will be aligned with the coordinates, the axis. So you want to maybe just make it a little bit more complicated by rotating these fake dimensions. So then you also know your effective dimension because it's just the dimension of the original problem. So that's how I can easily induce this kind of structure in any test set. So what do we find? Here I compare applying Baron, which is a state-of-the-art global optimization solver, applying Baron to the original, these problems with fake dimensions without any random embeddings, and then applying the random embedding framework. I assume I know DE, I know my effective dimension, and I only do one random embedding. Then I grow my ambient dimension, okay, of my test problem. So I try 10, 100, 1,000. And what we see is that the success of the solver goes down when I apply it directly to the problems, while if I apply it through one random embedding, it stays invariant with the growth in ambient dimension. Similarly, when I do some sub-part of the solver, it doesn't matter. And here we look at the CPU. Again, this grows for the solver applied directly to the problem. Similarly, if I do some globalized version of a local solver called Nitro, there I don't see, because it's a multi-start variant, I don't see such change when I grow the ambient dimension, but I see it when I look at the evaluation and the CPU time. Not bad, I would say. What about if I have constraints? If I have constraints, then I'm looking for, again, when does my red line of a random line intersect a subspace of global minimizers of my original problem. And now I do have this box. So what can happen, of course, is that this line for sure, it will not with probability 1 intersect the blue line, right? It could point this way, and then I am not intersecting in this box. So in this case of constraints, multiple random embeddings are needed. I'm still targeting a global minimizer inside the domain, but these points P could get close to the boundary, and I could have, this domain is in R big D, sorry, R big D here, and so I am bound to see effects from the ambient dimension coming in. So does this remain polynomial? So again, we looked at I have to again look at this probability of success, but now I have to be in this box. So we can again quantify this and bound it away from 0. And with asymptotic analysis, as ambient dimension grows, we can quantify its dimension dependence. And again, in general, I have a exponential term here, 2 to the big D, that shows that in some cases at least our quantification of it is not polynomial. However, there is a case when this is polynomial, as we were able to show. So if I draw my subspace kind of in a well-centered point, and if my minimizer is far away from the boundaries, so I have enough size of this subspace inside the feasible domain, then we can show, as you can kind of expect, that this would be polynomial. And then what happens is that this term completely drops off, and we only have this big D ambient dimension appearing to power DE. Here again, multiple dimensions are needed. Okay, so what happens if now I do performance profiles on the same test set with multiple random embeddings? So each plot is for a different ambient dimension, a big D. So for this case, I can see that when the ambient dimension is small, the solver, the unrandomized solver does fine. But as the ambient dimension grows, the higher the curve, the better the solver. You can see that the subspace variants start to do much better than the original algorithm. Similarly for nitro, and for nitro, because it's also a local solver, we even tried local solvers in the subspace with a little bit of randomization if you get stuck. And you can see that those local solvers, so even solving locally in the subspace with some mild, as I said, way to get yourself unstuck, that even beats these global solvers in the subproblem and definitely overcome the original algorithms. Now, what about, but this is just really vanilla. I mean, I'm just doing random projections. What if I'm trying to do something that's more problem informed? Can I choose these subspaces so that I try to learn my effective subspace at the same time? So in this case, this matrix A that before was just Gaussian or a random matrix is now using problem information. So how can I choose my A such that it captures the directions of variation of my function f? So we go back to kind of the definition. So how can we view these functions with low effective dimensionality? Well, they vary. So if I take any x and I decompose it into its projection onto the effective subspace T and its orthogonal complement, this function is invariant to all these components in the complement. I can equivalently write this as f of x. There is a function g such that f of x is g of z, where, so I do a change of variables, where these z lies is just the components of a basis u of my effective subspace T. So if I have a basis of my, if I had the directions of that generate my subspace T, then I can immediately reduce my problem, as I was saying at the start of this. I can reduce it and just solve it in the effective subspace. But of course, I don't have U. So how could I get this U? Well, if f is C1, we can apply this active subspace approach. So this is a very well-known technique in statistics, and it was very much brought and summarized and extended by Konstantin in a book called Active Subspaces. And what you do is you look at the moment matrix of the gradients. So this gradient, sorry, this is grad F transpose. I have a typo there. This expected value of the second moment of the gradients, this matrix here, effectively can be shown to generate my effective subspace. The leading part of this matrix will, the D times DE part of it will generate my, so the leading DE eigenvectors and eigenvalues will generate my effective subspace. And the range of that is the range of my effective subspace. So of course I have an integral here, and I have a distribution. I have a measure on my space. So you may say, wait a minute, I'm completely confused. I have an f that's deterministic. Where is the randomization coming in? It's coming from the fact that in the parameter space, I'm going to put a distribution on my parameter space. So I'm going to look at my variables x, as if I have some measure on that space. So you can think of it like I'm going to, I don't know, even uniform sampling, you can think of that, or a Gaussian or anything like that. So that gives you this row here. And then the expected value of this gradient transpose matrix is closely connected. So you can, but of course you can't calculate the integral. And so what you do is you sample. So you can sample discretely. You can do some MC, some Monte Carlo. You can sample some points in your domain, and then construct this matrix from sample averaging of gradient values. So you need gradient values. It's no longer a completely black box, but you get something very important. So what you can do is you sample discretely. The rank of this matrix will be at most DE. So when you start with a small m and you keep growing it, it may be less than DE, but then it will eventually reach that. So our aim was to get a bound on how many sampled gradients do you need to generate this approximation to the effective subspace, so to generate this active subspace matrix. And we proved that you need at most DE log DE. Of course, you need at least DE as well, because you want to have a matrix that's rank DE. And I will finish very soon. So then what we do in the algorithm, we go back to generating our matrix A, K here, using this kind of C hat information. So one option is I can spread my points in the domain, calculate gradients, form this moment matrix, and then do an SVD on it. Take the matrix of eigenvectors, and that's your AK, right? But the leading ones, just the leading ones, and then solving that reduced subspace. We also you can do it online. Take a gradient, solving that. You can decouple. You don't have to do gradient transpose. You can just look at the span of this gradient matrix formed of randomly generated gradient values. So you can take one at a time, one gradient at a time. So you solving that, you randomly do another gradient with Gram-Schmidt, orthogonalize it to the previous gradient, and keep increasing your matrix that way until you, especially with global optimization, you will see that the function stops changing. So then, of course, we have almost sure convergence again. The probability of success, it's all dependent on the ambient, it's not dependent on the ambient dimension. And then we can see how this compare between random subspaces and active subspaces. So is it worthwhile to spend this time calculating them or not? So I refer you to my paper. I had a lot more to say, but never mind. Thank you.